In this video, we're going to look at the stresses and deflections due to torsion. Most of the cases that we'll look at, or the most practical cases, involve circular cross-section. And so we have some fairly straightforward equations for that. The maximum shear stress in a shaft of a circular cross-section is simply Tc over J, the torque times the radius of the shaft divided by the polar moment of inertia. The angle of twist is equal to TL over JG. So we've involved now the length, the polar moment of inertia, and G, the shear modulus of the material. So we've used C instead of R because often we'll use R as the radial coordinate within the shaft. So R can vary from 0 at the center of the shaft to C at the outer surface of the shaft. And to calculate the polar moment of inertia, we can either use pi over 2 times the radius to the fourth, or in terms of the diameter, it's pi over 32 times the diameter to the fourth. So let's look at an example. We picked a 1-inch diameter shaft that's 3 feet long. We've made it out of steel, so G 11.5 million psi, and we'll apply a torque of 1,000 inch-pounds to the end of it. And so calculating a value of J and then plugging into the equation, we get a value of a little over 5,000 psi. We're going to look at the finite element model of this, and just one note here that what the FEA plot shows, it doesn't actually show the shear stress, but it shows 2 times the shear stress. And the reason for that is when we talk later about ductile failure criteria, it turns out you can compare with the maximum shear stress criterion, you can compare the yield strength of the material to 2 times the maximum shear stress. So let's take a look at our model here. So again, 1-inch diameter shaft, we've just fixed it on one end and applied a 1,000 inch-pound torque to the other end. And if we look midway along the shaft, we can see the stress distribution within the cross section. So 0 at the middle of the shaft, and linearly proportional to the radial coordinate, the stress will hit its maximum out at the outer surface here. Okay. Now we can also calculate the angle of twist. And in this case, remember that all your units will cancel out, so what you'll have will be in radians. If you want to convert that to degrees, it's a little less than 2 degrees over this 36-inch long shaft. Okay. Now, as I said, if you're designing something, a shaft to resist torsional loads, you're certainly going to pick a circular shaft. But often you might have a different cross section that's been selected to, let's say, to resist bending loads, and because of how the loads are applied, it ends up being subjected to torsion as well. So it is necessary to be able to calculate the stress and the angular displacement in different cross sections. And so for a square cross section, there's a tabulated values of that. And for the maximum shear stress, comes out to 4.8 times the torque times the side dimension cubed. And we can still use the same equation for the angle of twist. However, this value of K is called an effective polar moment of inertia, and for this square cross section, it's a to the fourth divided by 7.11. And by the way, these dimensions were picked so we can make a comparison to the circular cross section we looked at earlier. So this has the same cross-sectional area here. And so we calculate the maximum stress of 6,900 psi, so a little bit more than what we saw for the circular cross section, and the angle of twist is a little bit greater as well. But we're still in the same order of magnitude as far as the stress and the angle of twist. So looking at the FEA model for a square shaft, we can see once again that we have 0 stress at the center of the shaft. The maximum occurs at the midpoints of the sides, and very low stress in the corners out there. So that's kind of the main difference between this and a circular shaft, is that if we inscribe a circle within that rectangle, we'd probably be relatively close as far as the shear stresses go, because the material that's out in the corners really doesn't add much to the ability to resist the stresses. Now, one method that is very effective at making an efficient shaft is to use a hollow shaft, and of course most drive shafts are going to be hollow. And it goes back to the fact that the polar moment of inertia J is a function of the radius or the diameter to the fourth power. So the bigger you can make the diameter, the more efficient it's going to be. So this has an arbitrarily selected 2-inch outer diameter, and we pick the inner diameter such that the cross-section area here is the same as it was for that 1-inch diameter solid shaft we looked at as a baseline. Now, because it's circular, we can use the same circular shaft equations. Just our value of J has to include both the outer diameter and the inner diameter. And so we come up with a stress of 1460 psi, significantly less than the 5 to 6,000 that we saw earlier. And the angle of twist is greatly reduced from about 2 degrees down to about a little over 1/4 of a degree. So if we look at the finite element model of this hollow circular shaft, you can see I put a solid end cap on it just to be able to apply the loads a little more easily. But when we look out at mid shaft here, you can see that there really is no low stressed area, which is why this is a very efficient design, is that most of the material in the shaft is being stressed to a relatively high level. So the value of the stress is still linearly proportional with the distance away from the center axis, and because of the fact that the thickness is relatively thin, then there's not much difference between the stress at the inner surface and at the outer surface. And in fact, we can use an approximate method that works for thin wall hollow shafts, and it involves the mean area that's contained within the mid thickness of the shaft. And so in this case we take the average diameter, and if we look at the area that's contained within that average diameter, that's what we call A sub m, A mean. And the thickness we've calculated here, and so plug it into that equation, we come up with a stress of 1360 psi. So a little higher than what we got with the circular equations, because this is again an approximate method, and in particular the assumption is, because it's relatively thin, that the stress is the same throughout the thickness. Now let's find the angle of twist here. Kind of skip through that pretty quickly, but you can see it's not really much different than what we got with the circular shaft equations. It's still about 1/4 of a degree. Now, a nice thing about these equations is that they work for other shapes as well, as long as you have a closed hollow area. So in this case we're looking at a square cross section, and again we use exactly the same equation. In this case the mean area is that contained within the mid thickness, which is just this square area here, and calculate the wall thickness, and we see a stress of 1340 psi. So a fairly efficient shape. It's not round, but as long as it's hollow and closed like this, then it's a fairly efficient shape. And we can also calculate the angle of twist here, and again about 1/4 of a degree. So not much difference between the hollow circular shaft and the hollow rectangular shaft that we looked at. Where we do see a big difference is when we look at an open cross section. So in this case we're going to look at the same circular cross section we looked at before, but assume that there's this thin cut running all the way along the length. You can also think of it as if this shaft were made by rolling a piece of sheet metal and then welding a seam along the length. If that weld were to break, then we would have this type of a cross section here. And to be able to analyze this, what we do is use these approximate equations that are really the equations of a thin rectangle. And so it really doesn't matter what shape we have. If it's a thin geometry, then you can approximate it as this rectangle. So just like if we took this circular cross section and laid it flat, those would be what our values of A and B are. And again, this is an approximate method and works pretty well as long as the thickness relative to the width is less than 0.1 or so. So in our case, we calculate the shear stress with this formula, and it comes out to about 28,000 psi, which if you compare it to the closed hollow cross section, it's about 20 times greater. And so to understand why that is, the FE model helps out a little bit. So when we look at the stresses in the cross section, you can see that instead of well, you can see they're high both on the inside and the outside, just like they were with the closed cross section, but in the middle of the thickness they go to 0. So what it amounts to is, if you want to think of it this way, that almost think of it like water in a pipe, that the shear stresses can't flow all the way around like this, so they have to kind of turn around and come back. And so the distance that goes into your calculation of a moment that's necessary to generate the amount of torque, the distance between the opposing shear stresses is very, very small here, as opposed to if this was continuous all the way around. And if we look at the angle of twist, then the difference is even more significant. In this case, we come up with 38 degrees, and that's more than 100 times greater than if we did not have the cut there. So the lesson from this is that open cross sections are very poor in torsion, and so as we said, you would never pick a shape like that to transmit torsional loads. But even something like an I-beam, which again is selected to resist bending, but if it's going to be subjected to some torsional loading because of how the loads apply, you do have to be very careful, because you will end up with some very high stresses due to torsion applied torsions here.